kind of marketing and advertising for them. So here's some programs I was working on. So that's hard. That's really a lot of work into this. Here's another one that I was working on.
Are we use that next year?
Yeah, no, I mean, as long as you agree that this is worth the registration fee.
Make sure it's.
Work something out. Okay, so my business is called Mountain Air Engineering. It's just me. I'm working on this biogas project that I'm going to present on mostly today. And I also make emissions equipment for measuring emissions in different combustion sources. And I'm also the convener for Working Group 3 of the ISO work group to make standards for field testing. Some people are also in that group. BJ is. I don't know who else in this room is. But it's been very challenging for me. It's definitely not my expertise. We're dealing with over 20 countries, almost 90 people. We sent the draft document out for review. We received 110 pages of comments, over 800 comments. So we have to address all the comments. All the comments are disagreeing with each other, and just try to coordinate all the people. It's been very challenging, but we're making progress, and we'll be glad when it's all over. I'm also starting to do some local water quality work. I'm working to become a river steward for the Native Fish Society for the Coast Fork Plan. Yeah, that's fun. So the biogas project, for the partners, there's me. I'm doing the field work, providing the equipment. Cheryl Wine, she's currently a PhD student with Dr. Tammy Bond in Illinois, but she's transitioning, and so she's a large component in this project. Leaders Nepal, that's a group in Nepal led by Amod Pokro, who he lives in Berkeley, he's a professor there, but he's doing this air quality study. He's basically linked us up with the biogas projects in Nepal. He's working in an area where biogas exists, and so he's introduced us to the communities. CRTN, Center for Rural Technology in Nepal, they're our team in Nepal that's helping with the field work. They're doing a great job. And then University of Illinois, that's Dr. Tammy Bond, and then her postdoc, Nick Lamb. They're doing the filter analysis, and they're also just helping with ideas, kind of giving input, guidance of the project. And the Waltech Systems, he helps with the electronics, with all the equipment. And then the funder is Global Alliance for Clean Coastos. They're kind of managing the project. And the Climate for Clean Air Coalition also put up the money to do the project. So this is a grant from GACC and CCAC. So we're measuring biogas emissions. So here's a picture. This is from the manual from the 90s of the digester systems that we're measuring. Basically, it's just a concrete tank in the ground, and then it's connected to this mixer where they're mixing the cow poo with water, and then it's also connected to the toilet. In other projects I've seen, the toilet connection is not culturally appropriate, but in this place they just connect to the toilet. All of them have the toilet connected, and everybody seems to be okay with it. That's a picture of the mixture unit. So this mixture unit is empty. They're using the brick as a valve, and so they put the manure in there, and then they add water and they stir it up, and then they let it go down into the digester. And then that's a picture of one with poo in it. And then, so here's a picture of the whole system. That's the mixer. The toilet is right next to it. That's the top of the center of the dome where the gas is coming out. That's the shutoff valve. And then this is the outlet. And so the sludge just seeps out there. So they can take and scoop it out, or they can just let it seep out into the ground there. But they definitely take the sludge and put it on the garden. So this is, you can see this yellow pipe here. That's about the only change that's happened. So this area was devastated during the earthquake. And so a lot of the galvanized piping is no longer working. But they replaced the galvanized piping with more modern, like yellow gas line. That's about the only change these systems have had in the last 20 years. That's a picture of the system I built at my house to try to test my sensors before the project. And so that's a picture of the system that was just getting online. It's now functioning. This is this tube is now full of gas. And if you want later, you can come out and see it. We can cook something on the biogas stove. It's pretty fun.
Where do you get the feedstock?
Oh, I got started. I got manure from my neighbors because I think cows have the right microbes to start the colony. But then now that it's going, it's easier for me to just use grass. So I'm just using grass from around it in my compost waste. So the goals are to measure black carbon. That's the main purpose of the contract. Measure black carbon emissions in uncontrolled situations. So that means you gotta be measuring black carbon. We're doing it a couple different ways. We're also measuring other emissions, which we need to do to calculate the black carbon metrics. And then we're also measuring fuel consumption and usage to project those emissions to village-wide scenarios and more region-wide scenarios. And more than just what the purpose of the project is, I did this project because I was looking for excuses to work with biogas. I think biogas is a great idea, and I'm just really enjoying learning about it and learning about why isn't it happening in more places. It's happening in a lot of places, and it seems to be working really well. And I'm just curious to learn about the limitations and applications and why it's not being used more or how it can be used more. So we're measuring stove usage. So we're not using sums, we're using digits. I brought one here just so you can see. I recommend these. They're like a sums, but they're cheaper, and they have a point cell battery that is replaceable. So, the problem with sums is after you use them for a couple of years, they go dead. So this is what it looks like. It's a sums about the same size, but it has a USB stick on it. So you can just plug it into the computer. I put them in, you just want to make sure you wrap it in tape so it doesn't short out. But I think they're working great. They were recommended by Andy Grishaw at North Carolina State University. They're digits from LabJack. We're also measuring household fuel consumption. So we're using scales to measure the fuel wood that they're weighing. And then we made these things. I didn't put a picture up there since I had the real thing. I'll just show you. So it's just basically a flow sensor and a pressure sensor and a temperature and humidity sensor. And so you connect it into the gas line. So it's just logging when the flow is happening and how much it is. Sarah is here. She helped to make them and to calibrate them. And so she came just to make sure she was appropriately recognized for her contribution. They're working great. I don't know how long they'll last because of the corrosive nature of the acid in the biogas, but for this season we got amazing data from them. And I'm going to keep trying to use them. So the emissions equipment, basically we're measuring CO, CO2, and then the optical properties of the smoke, like how much is it absorbing light, how much is it reflecting light, to try to understand the radiative forcing when that smoke gets into the atmosphere. So we're using this Humatron system. So I built this when I was a graduate student at the University of Illinois. The main thing that makes it different than other equipment is a dilution sampler. And so it conditions the sample to be representative of what it's like in the actual atmosphere. So we're using this partial capture probe that also makes it very portable. So that's a diagram. I'm not going to go through the whole diagram, but that's the equipment. And so we put it in to measure the stove. So you can see the stove there, that's a wood stove. But we need to measure more things than this device actually measured. So for this project, we added some more equipment. So we added the TAP to measure the tricolor absorption photometer to measure real-time black carbon. And then, but we also need to measure the real-time background PM because we're measuring clean stoves here in a dirty environment. There's other stoves burning. So we gotta try to figure out what smoke is coming from the stove, what smoke is coming from the food that's being cooked on the stove, and what smoke is coming from some other stove. And then we also need to be measuring the flow of biogas during the test. So we put the same sensors in that box into this box to be measuring during the emission measurement. But then we also need to be measuring the composition of the gas. We need to know for the carbon balance purpose how much carbon is in the gas, but also we need to know the energy content. So we're measuring the percent methane, percent carbon dioxide in the fuel, and we can calculate whatever the remaining balance is. And so we added this little loop in there. It ended up getting pretty complicated. The methane sensor, well, I'll talk about it in a second. But that's the system we're working with. So that's what it looks like once it's installed in the house. You got so there's a biogas stove, and there's cooking on the pot. Let's see, so here's the line coming in from the digester. It's going to a valve. So we're running that tube through our sensor and then back to the stove. And then here's the Fumitron. And so here's the probe over the stove. It's a multi-point probe, and then the sample is being drawn into the Fumitron to measure the emissions. And a little sample is split off to the tap to measure the real-time black carbon. This is another picture. They're heating up some milk to make tea. It's just the same idea. We ended up utilizing a brick and corn cob to mount this probe. So here's a picture of a wood stove. It's the same equipment. We had to tune the equipment was originally designed for wood stoves, which are really smoky. So we had to make a lot of adjustments to make it more sensitive to measure the biogas. But we had to do baseline measurement of wood stoves also. Here's another picture of a wood stove. You can see our probe up there. So yeah, like I asked them, these two houses were using wood stove. It's like, why are you using a wood stove? Because their digester, one of the other ones, the previous house, their digester sustained damage in the earthquake that was not repaired. And then this house, their whole house was destroyed, so they're living in just a shack that they put together, and they're building a new house. So once they get a new house built, then they'll have biogas again. Here's an example of the data. So this, I combined the data from the flow sensor and from the digit data from the temperature logger at the same time. So the flow data is amazing in terms of usage. It's actual usage. Anytime you're measuring temperature with the temperature logger, there's always like it's a lot of work to I don't know if anybody has experience trying to analyze SUMS data. It's a lot of work to try to understand what the actual usage is from that. So it's really neat to have exact usage. We're knowing exactly when they turn the stove off and on and what the power level is. And then we can actually see like how good is the SUMS data, because you can see some differences. But for the most part, I mean, it makes sense. They agree well. So here's a picture of the flow data with also the composition measurement. So the CO2 sensor is an LED. It's on all the time. So basically anytime, so during this test, they cooked 4 different things. They kept turning the stove off to switch pots, and they turn it back on again. So the blue line is the flow. And slowly, and since it's a fixed dome, as they cook, the power level usually kind of goes down throughout the test. But in this case, they turn the stove up higher. And then the composition of CO2 is pretty much constant the whole time. But then see what happens with the methane sensors, they can't turn it on all the time because it's an incandescent filament. So if there's a combustible mixture in there, it will explode. So basically you have to have that sensor off. You turn on the equipment, you let the equipment run for a while until all the oxygen is purged out of it, and you have pure biogas. Then once I see that happens, then I can turn on the sensor. And while the sensor's on, I have to be there watching to make sure the cook does not turn off the stove. Because if she does, then there's going to get oxygen in there and it's going to explode. I don't think the explosion would be dangerous. I think it would just ruin the sensor box. I haven't tested that to make sure. So basically I turn the sensor on, I just sit there and watch it, take a sample for about 10 minutes and I turn it off. So I don't really feel comfortable like distributing this equipment to other people. Like this is kind of just a prototype and I'm trying to figure out how to use it. So I've just been using it myself lately, but it's working great. But the composition of the biogas is about the same for all the digesters. It's very consistent, and even for the digester of my house, it was just within 5%. You know, we're looking at like between 20 and 30% carbon dioxide, and between like 50 to 65% methane. So here's the example of emission data. It's pretty noisy because there's wind blowing the plume around, and also because a lot of times they're using steamer pots. pressure cookers, and the pressure cooker will steam off. And when it does, it displaces all the emissions. So then you're just sampling like steam for a second, and then it'll stop steaming, and then the emission will come through again. So there is a little noise in the data because of that, but the way that we're calculating emissions is still averages out, and it works fine. Because we're taking the ratio of emissions. So as long as the emissions are all diluted equally, it doesn't affect our calculations. And so in the bottom data, so that's carbon dioxide and carbon monoxide, the gases. On the bottom is the absorption. And so what's happening here is, so they started the test here. You can see they're burning the stove. We're getting lots of CO2 and CO. But then there's no, so okay, this is basically this is a proxy for when the real-time smoke is happening. But then so during the first part of the test, there's absolutely no smoke. The stove is burning clean. But then right here, we get this huge thing of smoke. So what happened there is they lit the stove outside the window, and the smoke started pouring into the house. And then, so that happened till here, and then they, that stove starts to die out. And then here, they put on a pot of oil. So basically, they're about to fry some potatoes, like in vegetables. And so the oil starts to heat up. And over the period of several minutes, it gets hotter, and the oil starts vaporizing. And then you're seeing this other plume of smoke, and then they dump in the vegetables and cook them. And so basically, my point is, at all these events, the stoves are burning clean. All the emissions are coming from somewhere else, not the stove, or from the actual what's being cooked. That's true for biogas and LPG tests that we did. So the conclusions are, the stoves are clean. When the stoves are actually burning, they're making the air pollution in the room cleaner because the background air has higher smoke than the actual stove. So if you calculate the emissions the same way that we've always done, where for wood stoves, where we subtract the background, we're actually reporting negative emission factors. So we got to think about how we're really presenting this data and how we're doing the calculations to present it in a meaningful way, because the stoves are literally cleaning the air inside the house when they're on. And they're all, the other issues, they're only used for cooking. So they, all these houses have animals, and they're always cooking every day, several hours a day. They're cooking food outside for their animals on a wood stove. So that's something to be aware of. You're only addressing like 25 to 50% of their energy consumption is happening outside on a wood stove. So even though they're clean cooking, that I don't know how you're going to get that energy to change. That's pretty, like there's no way they're going to be able to have enough biogas or afford the amount of energy it takes, I think, to cook outside. So then the other thing take home point for me was, it was really inspiring to see these systems, 20-year-old systems working great. Like they're functioning, which is barely any repairs. Like all the parts are original. The people are happy. The systems are amazingly simple. Like it's just real inspiring to see the potential. So other measurements I was doing besides the emissions, I was measuring the sludge temperature. I got an average of 26.6 degrees Celsius, which is pretty cold. Like if anybody knows biogas, the optimum temperature is like, 35 or something? So basically these systems are they're pretty big. They're like 6 cubic meters or something for a residential system, and then they're just going with whatever the ground temperature is, and they're working great. So I don't know what percentage, if you were to heat that digester up, how much more gas you get out of it, but that's something, what?
Or insulated,
Yeah. I was measuring the pH. I didn't get to do any pH measurements in the field, but I did a lot of pH measurements for my system when I was getting it online to figure out what I should be adding to make sure it was going to work and it wasn't going to flop. The tank pressure is another thing that in the future I'm going to be trying to measure more, because I was measuring all the pressure on the other side of the valve. And then also the feedstock input to try to get a better idea of the performance, like the efficiency of the digester, to know the seasonal variability, and also just to try to understand how it could work in other regions and climates. So in the future we're going to do more measurements. This is the monsoon season. We just finished the measurements a few days ago in Nepal. I'll be going back in the winter and then in the spring to try to measure seasonal variability. And one interesting thing for me was, like, I want to help these people. That's my main reason for doing this work. And this project was weird because we're paying the people for their time. We're inconveniencing them. We're in their house with this equipment. They don't perceive us as helping them at all. which makes sense. We're just like, hey, can we go in your house and do these measurements? And so I've really made a point of talking to everyone to understand how their systems are working. And a lot of them did need little repairs, so I didn't really have the time this time to make the repairs, but I'm keeping a detailed log of how each system is performing and what repairs need to be made, so I can help them, optimize their systems when I return. I did like unclog a few people's stoves, and that seemed to make a pretty good difference while I was there. So in the future, I just want to understand like what other needs are there for doing monitoring. Like I had a project, I had to measure these things, so we made equipment to do it. But I've been started to look at other carbon financing projects, and the ones I've looked at, they're calculating carbon credits just based on the average number of pounds per household. Like that's how the carbon credits are determined. So there's a lot of really rough calculations that are happening to determine the carbon credits saved from these projects. And so I'm interested to look at that methodology to see if there is room for improvement, like if it's worth the cost of actually trying to monitor some things better. And then just install more systems. I would like to make my system functioning better so it'll work during the winter. Right now it's going to die when it gets cold. And also in other places, like I'm really interested to continue working in the fall to see where other systems can be installed. This area of interest for me is to make emissions equipment. I'm not going to go into it now, but I'm also I'm building equipment for a professor in China right now, and then I'm also, I've built equipment like this in the past for measuring cook stoves and brick kilns. This is a picture of a kiln in Nepal, and that's just a couple of pictures of the equipment. It's just a really versatile equipment. It's not very cheap, but that's another interest of mine that I'm working on right now. That's all.